Derivatives are useful. But why are they useful? Well, there are many reasons why they're useful, but one reason is that allow us to find the max or min. In other words, they allow us to optimize. So this is climb time, and in this video, we're going to look at a specific example of optimization. We're going to look at how to optimize volume of a box. All right, so let's say we have a rectangular piece of sheet metal. It is 10 inches by 15 inches, and we are going to turn it into a box. We're going to do this by cutting the corners of the box, and we want to make a box with the biggest volume possible. So that is the problem we're looking at. Again, it's 10 inches by 15 inches. We're going to go through the process of how to use calculus in order to find the maximum volume that we can create out of this box. So we start by looking at what would it mean if I cut out the corners. So if I cut out the corners, that means I'm going to cut out a little box there and a little box here. I'm going to cut out a little box here and a little box here. If I cut out a little box out of each one of those corners, I would be able to fold up the edges. So imagine a crease here and a crease here and a crease here. So good I am at creating a straight line. Hey, not bad for me. And a crease here. All right. And then I'm losing markers. I'm gonna have to go pick those up. So I cut out the corners. I have 4 corners there, and I fold up these flaps, and it's going to create a box. But these 4 corners are going to be gone. I won't be able to use them anymore because they're just gone, thrown away. But what's left over is going to be a rectangular base. And then there's going to be a flap up here that's going to fold up to create one side wall. That's going to flap down here. That's going to fold up and create another side wall. And then this is going to be a side wall and side wall. So we're going to have 4 side walls, and we're going to have a rectangular base there. All right, so the question is, how do I find the maximum volume? So whenever you're doing an optimization problem, the first thing you need to do is probably have a diagram. Diagrams are going to be essential. It's really hard to solve these problems without a diagram. So you need a diagram. So we have a diagram. And then the next thing you need is an equation. Without an equation, it's hard to optimize anything. So we need an equation for volume. So I'm going to write down equation for volume. So volume, I know, for a box is going to be length times width times height. There's 3 parts to a box, 3 dimensions. So I'm going to say length times width times height. So I need to find the length, the width, and the height. So let's go back to here. So if I don't know the size of the corner, I'm going to call that X. So X is going to be this unknown size for the corner that I'm going to cut out of each corner. And each corner is going to be cut out the same way. So while I don't know exactly what X is, I do know that X is going to be the same for all 4 corners. So if I look at the base here, this little rectangular base over here, this base is going to have one dimension, which I might call that the width, is going to be 10 minus X minus X. So if that's X, and this is X here, then I know that that part here that's orange is going to be 10 minus 2X. Because I subtracted X from each side when the total length is 10. In the same way, I can figure out what the, we might call this the length of this base is. Length of the base, oops, I went too far with there. There we go. The length of the base is going to be similar. If I can erase that. It's going to be 15 minus 2X. So I have 15 minus 2X. Okay, so I get 15 minus 2X for the length, 10 minus 2X for the width, and then the height, if it folds up, the height is going to be X. That's what the height's going to be, because that little part, this little flap that gets folded up, it's going to be X high. So height is going to be X. So now I can create an equation for volume with one variable, because that's what you want. You want it in terms of one variable. So the volume is going to be the length, which is 15 minus 2X, times the width, which is going to be 10 minus 2X, times the height, which is going to be X. So now I have an equation for volume in terms of one variable. Now it is common that we have multiple variables here. In this case, it was pretty easy to get all our variables in terms of X. But what you want is one independent variable. So sometimes you have to use constraints that you have which basically means additional equations to be able to plug in for the variables you don't want so that you have just one independent variable here. So we have the thing we're trying to optimize, which is volume, and we have one variable that it depends on. In this case, it's x. So what we want to figure out is what is the max volume based on x. So I have control over x. I can determine how big of a corner to cut out of each corner, how big of a little notch I want to take out. I have control over that. I have control over x. That's my independent variable. And then my volume will depend on that. So that's what you want to do. When you do an optimizing problem, it's really important that you can find an equation for the thing you're optimizing in terms of one variable. You want to isolate that one variable. So again, you may need a second equation to do that for many problems. In this case, we don't. We can just get x pretty much right out of the diagram. All right, so here's our equation. It's a cubic equation. This problem does give us other constraints, which is helpful to know. And it says that there are depth constraints, that the minimum depth is 1 inch. In other words, we can never make x smaller than 1. And the maximum depth of this box is 3. That means we can never make x bigger than 3. Okay, so this is just something that was in the problem. There's nothing that requires the minimum to be 1, the max to be 3 in terms of the physical constraints of the piece of metal. But that's something just that the problem included. All right, so something that's also helpful to do before we move on is to graph now the function. Since we have a function for volume in terms of x, it's very helpful to graph this. Now, you can use a graphing calculator for this. You don't need to graph it by hand. You don't need it. It's a cubic function. Cubic functions a lot of times have 2 humps in them. But one thing we can do, we can just kind of think through this. When we look at the graph, we can see that it kind of makes sense. And that is that when x is 0, you're going to have 0 volume, which makes sense because if I don't cut anything out of the corners, how can you have volume? You can't fold up the sides, so it can't be any volume. And then you're going to get 0 volume another time, and that's when x is so big that it eats up the entire shorter side. And so when x would eat up the entire shorter side is when x is going to be equal to 5. Because if x is 5 here and x is 5 here, 5 plus 5 is 10, it eats up the entire shorter side. And so therefore you don't have a flap to fold up. So another volume, 1, 2, 3, 4, 5, another time when volume is going to be 0 is going to be at 5. And there's a third time the volume is going to be 0. And that's going to be when you eat up the longer side. So eating up the longer side would be if x takes up half the length here and half the length here. And since the entire length is 15, that would be at 7.5. Now, this is not necessary to do the problem to think through this, but it is helpful when you see the graph. You can just graph this in your graphic calculator. But it is helpful to when you see the graph to see why it makes sense. So it's going to end up going something like this. And then it's going to come back down again. It's going to look something like that. I'm not sure if the top is correct, but anyhow, it's going to look something like that. Now, because we're talking about the volume of a box, negative volume, and it actually goes through the x-axis like that. That's what a cubic function often looks like. A lot of times you have 2 of these spots where you get a local max, a local min. It's very common with cubics. You don't get every single case, but it's very common to get that. But because we're talking about the volume of a box, we know that it doesn't make a whole lot of sense for our volume to be negative. So, this is kind of like out of bounds because negative volume doesn't make any sense in this case. This is also, everything here is also out of bounds. So out of bounds here, out of bounds here. And so this is really the target area we're interested in. And even if they didn't give us constraints, we would have natural constraints. The natural constraint would be 0 and 5 because we can't have negative volume. That doesn't make any sense. So as soon as we get to 5, we have 0 volume. And before we cut anything out, we have 0 volume. So we got 0 volume at 0 and 0 volume at 5. And so these are our 2 natural constraints. So once you see the graph, once you see what it looks like, it's pretty obvious where the max is going to be. The max is clearly going to be at the peak here, wherever that is. And I don't know where that is yet. I have to find out where that peak is. But also let's put in our constraints that we have here. We have a constraint at 1. And so I'm going to put that in. We have a constraint at 3, which is here. All right. And I don't think my drawing is great because I know this problem already. 3 looks like a max, but it's not the max because I already know what the graph looks like. So anyhow, those are our natural constraints, one and three. And we're going to try to figure out, because we can't make, just because of the constraints of the problem, we can't make x any smaller than one, and we can't make x any bigger than three. So this is actually the graph of interest right here. That is our domain. So this right here would be our domain. And our domain is going to be when x goes between 1 and 3. So we could say 1 is less than or equal to x, which is less than or equal to 3. And it can include 1. It can include 3 in this case, because I did say the min could be 1 and the max can be 3. So another way to write this in interval notation looks like this. It looks like a point. It looks like a coordinate point. That's another way to write an interval for x. So x, oh, I made a mistake here. Because we can include 1 and we can include 3, it's going to be square brackets. Square brackets. Commas means you don't include the endpoints. Square brackets means you do include the endpoints. So it can be 1, it can be 2, it can be 3, it can be anything in between. So that's our domain. That's the values of x we're allowed to optimize this problem and to find the value of x between 1 and 3. That gives us our maximum volume. All right, so if they didn't give us these constraints here, we would have to say that there is a natural domain. The natural domain would be between 0 and 5. But in that case, we'd use parentheses because 0 doesn't make sense. You don't actually have volume at 0. 5 doesn't make sense. You don't actually have volume at 5. So you'd use parentheses instead of square brackets because 0 and 5 would not be included in that case. And that's kind of why I put parentheses by default, because a lot of times the endpoints are not included because we have 0 volume, which doesn't make sense. It's not a box at 0 volume. So you can't actually include 0 and 5, but you can have everything between 0 and 5. Well, because they gave us these constraints, we can put in 1, and 3. We can include 1 and 3. All right, so that's step 1 is to have a diagram. Step 2, maybe I will actually write these in. So step 1 is the diagram. Step 2 is the equation. Step 3 is a graph. Once you have an equation, you can create a graph. And then step 4 now is to figure out where the peak is. And this is where calculus comes in, to figure out where that peak is. So let's do step 4. Let's find the peak. And the peak is going to require us to do calculus and find a derivative. But first, what I'm going to do is I'm going to go ahead and multiply this out. So I'm going to use first outer inner last. So 15 times 10 is 150. 15 times negative 2x is negative 30x. Negative 2x times 10 is negative 20x. And run out of space, unfortunately. Negative 2x times negative 2x is positive 4x squared. And then finally, I have to multiply all this times x. All right, so it is a cubic equation. I know this because there's 3 x's we've multiplied together, so I should end up with a degree 3. It means my highest power for x should be third power. And so I'm going to give myself more space this time. So v is equal to, and I'm going to combine like terms and write in standard form. 4x squared times x is 4x cubed. And then we're going to have negative 30x minus 20x is negative 50x. And then multiply it by x and get x squared. And then finally, plus 150x. So you could put this equation in your graphing calculator and graph it if you want. It is kind of nice to see your zeros. There's a 0 at 0, there's a 0 at 5, there's a 0 at 7.5. Or you could put it in standard form first and put that in your graphing calculator. But you definitely want to put it in standard form before you find the derivative. But it is much easier. You don't have to use the product rule. So let's find the derivative now. The derivative with respect to x is going to equal 12x squared minus 100x, just doing the power rule on each term, plus 150. Okay, so that's the derivative. The reason why we're finding the derivative is the equation of all the slopes of all the tangent lines. This is the function of v with respect to x, and this is a function of all the slopes on v with respect to x. So it's all the slopes along here. And what we want to find is we want to find where the slope is 0, because where the slope is 0, that's going to be where our max is. That's going to be our peak. That's our optimized value. So this is where derivatives are useful. Derivatives allow us to find peaks, little local peaks, to figure out where it's going to hit the top spot before it starts coming back down again. Or it could be the other way. It could be the min, where it's going to hit the the lowest spot before it starts going back up again. So you can think all sorts of applications where this is useful. You can think in terms of business. You want to maximize your profits. You want to find the peak where the profit's going to be. You want to minimize your costs. You want to find the lowest spot. So finding a max, finding a min, those are very useful things. As long as you have a graph, you can take the derivative. And then what we want is we want to know where the slope is zero. So we set that equal to zero. So we say take b prime of x and set it equal to zero. So b prime of x, when is it going to be equal to zero? That's a question mark. And so what we're going to do is we're going to take this equation and set it equal to zero. So we take 12x squared minus 100x plus 150 and set it equal to zero. Now this is a quadratic, and a quadratic equation is a parabola. Parabola will hit the x-axis in two spots at most. Two spots. It could also hit it nowhere, and then you have no real solutions. That would be like a parabola shifted up, and so the x-axis is below it. You could also hit it in one spot if it's just tangent to the x-axis. So it's possible for there to be one solution, two solutions, or zero solutions. But you can see our graph. It makes sense that there's going to be two solutions, one up there and one down there. So there are different ways to solve this. The focus of this class is not algebra, but you could try to factor it and then set each factor equal to zero. You can use the quadratic formula. There are different ways to do it, but another way to do it is to actually put this into your equation. Say y equals, or put this into your calculator, put y equals 12x squared minus 100x plus 150. Put that into your calculator and then find the zeros. And that's fine too, as long as you're allowed to use a calculator for this problem. And generally with optimization problems, you're allowed to use a calculator. So however you want to find the zeros is up to you. I am going to go ahead and tell you what the zeros are. If you use the quadratic formula, it comes out to x is equal to, and there are two answers here, not surprisingly, 25 plus or minus the square root of 5 squared of 7, or 6. So that's an exact answer. And that exact answer can come out of the quadratic formula. I really like the quadratic formula, honestly, because factoring only works part of the time, but quadratic formula works every single time. So why not go ahead and use a quadratic formula? If you see that all three terms have something in common, in this case, definitely they have 2 in common, then go ahead and divide every term by 2. It makes it easier to do the quadratic formula. But the quadratic formula is definitely the best way to go about finding zeros when you have a quadratic. However, since you are allowed to use your calculator, and this is an applied problem, it's an optimization problem, it's perfectly okay to let your calculator help you find the zeros there. Now, what I wouldn't do in this case is let your calculator help you find the max, because the whole point of this problem is for you to find the max using calculus. So don't use your calculator to help you find the max. You can check yourself later to see if that works, but you can use your calculator to help you find the zeros, because again, the purpose of this is to understand how to find zeros. So anyhow, there are two answers to this. One is the one here, and one is the one down here. So the one that we are interested in is going to be, the first one is going to be approximately equal to 1.962. Okay, and so 1.962 is really close to 2. So it's like right here. It's very close to 2, and that is actually where we find our max. There's another answer there. The other answer is between 5 and 7.5. So you see there's a plus and minus. You're going to get 2 answers. The second answer is where the slope is equal to 0. It's just out of bounds. It's not within our domain, so we can disregard that one. All right, so the volume now. So the question asks, where's the max volume? So let's write that in. Where's our max volume? And so that is what the question asked. And so it wants usually an x and a v. And so we know the x is going to be at, and I'll say equals now, even though it's an approximation, 1.962. And now the volume at that spot, again, you can plug it back into your original equation if you want to and do it by hand, but not necessary. Use your calculator. You already use your calculator to graph this. And so then just use the trace tool. And in the trace tool, type in 1.962 in the trace tool, and it'll give you the exact volume at that spot. And it comes out to be, it looks like 132 inches cubed. 132 inches cubed. Okay, because everything's in inches. So that means if and it's interesting here because it didn't come out to be a nice round number. It's not like x is equal to 2. It's close to 2, but it's not quite 2. So if you're looking at the graph and you're trying to estimating based on tracing and say, where is that max? You're probably not going to figure it out. You're going to have to either have a calculator find the max for you or do what the calculator is doing, and that is find the derivative, set it equal to 0, and solve for x. Now, you don't have to find the values of x analytically or algebraically. You can go straight from the equation here to the values for x, but it doesn't come out, exact. Doesn't come out to be an integer. So that's why we actually need to do the analysis to figure out what x would be. So to get the max volume, it's going to come out to be 1.962 for x, and that's why we have to cut out the corners. And you might think, what does it matter if it's 1.962 or 2? Well, in business, sometimes this extra accuracy is a difference between thousands, tens of thousands, hundreds of thousands, millions of dollars. So, or even billions in some cases. So yeah, those rounding errors really do make a difference as you scale. So, so it's useful to be able to find out exactly what the maximum volume can be and at what X value can we create it. So another question they might very well ask is the min volume. So what is the minimum volume? Which is kind of a little bit of an academic question, because if they didn't put in these artificial constraints, the minimum volume would clearly be 0, because I would not even be creating flaps. As long as I create a flap, my volume grows. But they did put in those constraints of 1 and 3, and they say you have to have a minimum depth of 1, so x has to be at least 1, and x can't be any bigger than 3. So based on that, what's the minimum volume? Well, based on my little sketch here, it looks like it's 1. But you wouldn't know that unless you actually plugged in. And you don't have to actually plug in, but you should figure out what V of 1 is. What is that? V of 3, what is that? And you got to find those values. And once you find those values, you choose the one that is the biggest. And you don't have to do it manually by hand. You can put it in your calculator to find it. And I have V of 1 because I know that actually is the minimum. I also have V of 3 as well. So 104 inches cubed. And again, I just let my calculator give me that answer. And then this is 108 inches cubed. Okay, so you can see that the max volume is 132 inches cubed. And you can see at our minimum value for x, we have 104. The maximum value for 3, we have 108. So it kind of makes sense. It goes from 104 to 132, back down to 108. My sketch isn't totally to scale here. But that means your minimum right here is 104. So this is your minimum right here. And you wouldn't know that unless you actually plugged in and you have some sort of understanding what the graph looks like. So it's really helpful to have a graph. Again, you can let your graphing calculator help you with finding the graph. You can let your graphing calculator help you in finding the zeros for x once you take the derivative. But what you shouldn't do in this case, because the point of this problem is optimizing using calculus, what you shouldn't do is have your calculator find the max for you. You're doing what the calculator is doing. You're trying to learn how to do what the calculator is doing. Just like when you were first learning quadratic equations and how to solve that, you wouldn't let the calculator let you find the values of x. You'd have to learn the quadratic formula. So we're trying to learn different stages along the way. And the stage we're trying to learn right now is how to use calculus to find the x value of where that peak would be. And once you find the x value, which turns out to be 1.962, we use that to find the actual volume by plugging it in to the volume equation. But again, you can just let your calculator do the work. You can just trace, on that one, you can let your calculator do the work. You can just trace your function, type in 1.962 and put down your volume. You don't have to go and plug back into the volume equation. Anyway, so that's how you do an optimized problem. Those are the steps. I guess there is a fifth step here I should write down. Fifth step is right here, and that is checking your endpoints. So step 1, come up with a diagram. Step 2, come up with an equation based on a diagram, equation where you have one independent variable, and it might require coming up with a second equation and plugging back into the first equation so that you have one independent variable. So step two is one independent variable, three is a graph. So you have an understanding of what's going on and you understand a relationship between how X affects V. Step four then is to take the derivative, set it equal to zero, and solve for X. And there are two answers here, but 1.96 is the only one we're interested in. The other answer is about 5 or something like that. And then check that value. Now, if you know the graph, you know that this is the max already. But check that value and the endpoints, because there may be certain situations where the endpoints actually give us a greater max than the critical number. So those are your steps, and that's how you optimize using calculus.